Good morning, everyone. It's my pleasure to introduce Professor Moncef Gabbouj from Tampere University of Technology, and Dr. Moncef now is a professor of singular processing at Department of Singular Processing, and Dr. Gabbouj is also IUCRC fellow and has numerous awards and numerous titles. I cannot enumerate all of them here, but we are very excited to learn from him and also Dr. Jenny Rotohaji on a very advanced and a very cutting-edge development of the new novel machine learning solutions for pertinent applications. I think we will see a lot of very exciting projects. So without further introducing, let's welcome Dr. Moncef.
Thank you, Tianfu, and good morning, everyone. I'm happy to be here. It's my pleasure. First time I'm visiting NC State. Very beautiful campus and very impressive library, especially that it carries both of my books. I just checked that both of my books are in your library. Thanks, Hamid, for inviting me here and having me here today. I'm here with a couple of three people from Finland. My postdoc, Jenny Raitoharju. She will give the second part of the presentation today. And we have a couple of delegates from the companies in Finland. We came from an NSF CBDI meetings down in Lafayette, Louisiana. Kimmo Valtonen is CTO of Mbrain. And Matti Vakkuri is the head of research from a big company called Tieto, active almost everywhere in the world, especially in Scandinavia, Finland, and also in USA. So, a great pleasure to be here. My name is Moncef Gabbouj. I come from the Laboratory of Signal Processing, where I have been for the past 28, 29 years. Before that, I graduated from Purdue University in West Lafayette, Indiana. Many, many years ago, maybe before some of you were in high school or primary school, whatever. So it's been quite a while. Originally, I was working and still working on signal processing, and we developed the theory and applications of nonlinear signal processing from the beginning, from scratch in the 80s. And of 70s, 80s, and a little bit of the 90s as well. And then from there we moved to different other areas, and little by little we follow the trend. We are in machine learning, we are in AI solutions, but we have a special emphasis. Our emphasis on AI solutions is on signal processing. And I will show you in the next slide why we focus on signal processing. I mean, all these AI solutions that are provided today or being developed today, dealing with intelligent systems, intelligent houses, smart buildings, autonomous systems, they all have sensors. They all have signals that they measure, you know, from different types of sensors. And if you look at the bottom of the slide, then you got all types of different input sensors that go to your system. And this is where you have big data, you have analytics, you have multimodality. And then we organize our approach in processing this data in what we call a multi-layer hierarchical approach. So the first layer in this approach here describes what we do originally in signal processing. So we do noise filtering, we do sampling, we do denoising, we do representation, augmentation, all that stuff that you guys, if you're doing signal processing in electrical engineering, you have to do these things. So you have to understand that the sensor data is not misleading you, is not giving you the wrong values or like outliers. And that's the signal processing layer. We call it abstraction, description, augmentation layer, but again, it's a fancy name for signal processing. The second layer is the analytics layer. That's the machine learning layer. That's the mathematical optimization layer. That's where we get things done. But this layer is not going to act directly on the raw data as they claim all the time from deep learning and CNN, convolutional neural networks, because some of the data is garbage. So you need to go through a layer where you clean up your data and you prepare your data for your machine learning. And then after that you have the upper layer. I call it the interface layer to these guys coming from industry. They have different and specific applications in mind. They would like us to maybe design a surveillance system or a recommendation system or a management system for them, and they have a specific set of data, maybe one or multiple modalities from here. And that's how we sort of pull things up from the different available modalities through the signal processing layer, through the machine learning analytics layer, all the way to the application layer. And this is why I call our AI approach a signal processing, computer vision, pattern recognition based approach. What got us started a few years ago was our first work on optimization, mathematical optimization based on particle swarm optimization. Maybe some of you have heard this before. So we have a book out, and I checked, it is in your library, you can go and see it. And this optimization algorithm sort of expands and extends PSO into an area where nobody ever wondered before. The area is the following. In most cases, practical cases of optimization, what we call the solution space dimensionality. The solution space is where you're trying to determine what the optimal solution is. That dimensionality of the solution is not known ahead of time. And if you don't know that ahead of time, most of the optimization algorithms that you are familiar with do not work. But in this scheme, even if we don't know the dimensionality of the solution space, we can still solve the problem because we integrate this dimensionality issue into the optimization itself in a nice interleaved manner. And at the end of the day, when we solve the particle swarm optimization problem, we have a solution that is optimal parameter, optimal solution in the optimal dimensionality or at the optimal dimensionality. So if you want to know more about that, book is a good place to start. It was also translated in Chinese recently. I was in China last week, so I was advertising that as well. Well, this PSO, MDPSO, has lots of ramifications. Perhaps the most important one is this optimization problem for MLPs, multi-layer perceptron. All of you, if you ever used multi-layer perceptrons in your life, you have been just using a fixed topology network. Somebody tells you how many levels, how many layers you should take. Somebody tells you how many neurons you should take. Well, here we solve the problem of optimizing the network in two ways. We find the optimal network parameter, which are the biases and the weights, but at the same time, we find the optimal number of layers and the optimal number of neurons for each layer. And it's all solved in the same problem. It's not like a sequential thing. We solve one problem and then we go to the next one. No. It is an integrated, interleaved optimization algorithm. And believe it or not, if you look at this expression here, it encapsulates everything about this network. The number of nodes, the number of layers, the biases, and the weights. Everything is here. This is called a particle in particle swarm optimization. We let those particles fly in the space, and one of the particles will be the winner, and that one will determine the optimal solution. Then we embedded that MLP, which has a variable topology, and we optimize its topology in a classification problem, this time with ECG. So we're able to do some signal processing on the raw data from here, and after we have those features ready, then we go into the MLP inside this PSO-based, PSO-enabled, and we are able to solve that classification problem. We did this roughly 10 years ago. At that time, it was the state of the art. in that. We will revisit this biomedical signal processing issue later on. And then when I said earlier that we sort of migrated and moved to AI solutions and machine learning, I don't mean that we just go and take out of the shelf existing machine learning and use them. No, 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 no. We develop our own stuff. This is a CNBC. This is a new classifier that we developed from scratch that uses the network that I showed you earlier, this guy here. This is one unit, one module. We put it in every white box in here. Every white box has inside of it an MLP whose topology is changing in time. Wherever we have new data in, we have new relevance, like new labels, we train that network, we evolve that network. We were able to do the CNBC. It has a lot of interesting features like scalability with respect to features, scalability with respect to classes, and so on. Here's a couple of applications where we put that CNBC in. This is an EEG classification, so sort of brain signal, multiple channels, and we do an incremental learning. As our ECG is changing and dynamically all the time, these neurologists, these experts come in and make labels. As they make new label available, we take that into consideration and we evolve our network to recognize what is happening in the brain. Here's another application of CNBC in a bit different area. This is a SAR, synthetic aperture radar classification problem, where this is an example of the San Francisco Bay Area. You see, this picture is huge. This is thousands and thousands of pixels by thousands of pixels. And you see some of the markers here in different colors, a few of them. A very, very minute number of pixels that we manually label. This represents about 0.05% of the total amount of data we have. And believe it or not, that's the only data we use for training. When you read about CNN and deep learning, and given the data set, oh, we use 80% or 90% of that data set for training. No, here we use 0.05%, less than 1% of that data to train things. And see what we get. Amazing. We get everything. We get very accurate segmentation and labeling of the pixels. We're even able to capture a few things like a boat here, like a lighthouse in the middle of the ocean here. We're able to find all those things. Here we use two types of features. We use RGB type features from images, and we also use all the radars, aperture synthetic radar type feature, the gamma, the alpha, and all those parameters there. So it's really a successful, nice use. Now, I suppose many of you are using CNNs and deep learning or interested in this area. Before we go into that, I want to ask the question, what is wrong with CNNs? Well, there are a few things wrong. First of all, if I have an example like Panda here and I add a little bit of noise there, a bit sophisticated noise, I mean, visually it looks like a panda, right? I mean, we all recognize it as a panda. Except that one of the CNN recognized it as a gibbon. It's not a panda anymore. And there's some nicer, even more shocking example, like a school bus turning into an ostrich. You can find that in Google if you like. So there is a problem with CNN, with deep learning in terms, first, of complexity, problem in terms of interpretation, and the last problem is about overfitting. But that's a bit of a general problem in neural networks. If you're not careful on how to design your neural networks, then you can get this generalization issues. So we thought about this deep learning for a while, and I said, hey, if we look at the problems that a lot of people are solving with deep learning, perhaps we can solve them with shallow, very simple learning. And this is an example of a very shallow neural network that solves the problem of segmentation, learning to segment. It's called L2S, learn to segment. The idea is, given this input here, we learn to segment this input. We have the segment there, which later goes to an object detection or object recognition problem. And look at the results here. Look at the ground truth. Look at the L2S. This is our result. This is ground truth. They're extremely good. And this is an extremely simple network. This network has 450 parameters. And we compare the results in the paper. There's the results here. We compare this against this big CNNs with 134 million parameters, 160 or 155 different layers. So if you don't have to use a deep network, don't use it. If there is no need for a deep network, don't use it. Then the second issue is, or the second problem that we deal with is called object proposals. So in an image or a sequence of images, you may want to locate the object, and after you're locating the object, that's called object proposal. Then you will go to object detection and recognition, and then you go recognize what that object is about. So we're going to do this for like labeling. So you label what you see in the picture, or you also do a image like a object detection there. In this example, this paper in Neurocomputing 2017, we managed to combine machine learning, CNN in this case, with signal processing we call a structural edge detection. And I will show you some examples here. These pictures, these scenes are taken from my city called Tampere. And you will see on top there, we'll be running a text that you can see that's the content of the picture. That's describing what is in the picture. In the next video I will show you, I will box the object for you and label them. Okay, so let's see if that's working. So we're spitting out the text on top as we go along.
Where's the snow?
This is summertime. Beautiful summertime in Tampere. Welcome to visit. Lakes and green, water. Okay, let's go to the next one. Oh, in this video, there are a couple of frames that sort of attracted our attention. One says people and clothes on top here. And then if you look very, very carefully, you find a couple of people hiding there behind the flowers. And this guy here says there is a boat, and if you look very carefully, there is really a small boat. And just from that frame, it was able to capture it. The second video I'm going to run is a boxing of the object. And here you will notice that some of the mistakes are made, especially when the object is rectangular, so it may recognize it as a window or a door where it is not really a window or a door. And you could also see that it's really accurate. It's really, really nice. Okay, the last video I'm going to show you here is a bit more futuristic, and hopefully one day we'll be able to do this in real time, and that would be very nice for our autonomous systems, that we are able to capture all these objects while we're driving, or our car is driving us, and recognizing people and cars and trucks and buses and so on and so forth. So this is done not in real time, so we do the analysis and then we overlay the results on top of that. Okay, while a lot of people have been active in 2D CNNs, a lot of our effort lately has been focusing on one-dimensional CNNs. We are one of the few people who, I wouldn't say invented, but sort of proposed and promoted the use of one-dimensional CNNs. I'll show you a few examples. The first one is about motor fault detection. And in motor fault detection, we focus primarily on these bearings. These bearings in some expensive motors are very critical parts. And if they are not working right, and if they are getting like lousy, then they need to be changed on time so that they don't screw up the rest of the motor. If you look at this is the type of signals we're getting out of these bearings. The first three, the input signal, the bit expanded one, and the spectrum of that signal, if you compare the first three, the top three, compare them with the bottom three, visually you will not be able to tell any difference. The top three represent signals we get from a healthy bearing. The bottom three are from a faulty bearing. So visually we can't tell the difference. So what we did is we organized and we developed two types of network. We call CNN-I for inner ring of the bearing, CNN-O for the outer ring of the bearing. This is the outer ring problem. This is the apparatus we had in the lab. It's collaboration with our colleagues from Qatar University in mechanical engineering. And we were able to capture this data coming from wirelessly from the engine, from the bearing, and we were able to compute good probability values for a good bearing, a good like anomaly detection in the bearing, whether there is something wrong or not. So there is a paper here. You can check the results there if you're interested. The second problem that we dealt with, again, in biomedical signal processing, this is a patient-specific. This is everybody sort of has their own different type of ECG signals. So after the beat detection, we go ahead straight input that to the CNN, one-dimensional CNN, and we're able to get good results. In fact, when the paper was published, it has been one of the, it has been the state of the art. It has been one of the most downloaded paper from the IEEE transactions on biomedical engineering for quite some time, since it has been out in 2016. Now, I don't know how many of you are working in ECG classification. If you have data with abnormalities, with abnormal beats, then you could use that data to train your machine learning to classify good beats versus bad beats. But here's a problem where you don't have bad beats from a given person. If you have a healthy person with no history of cardiac problems before, then the heart is safe, is clean, no bad signals there, so you can't train your machine learning on that data. So what we do is we go back to our signal processing and we try to develop something we call artificial or synthesized abnormal beats. This paper appeared last year in Springer Nature's open access. You can get this paper online. So what we did is we look at the different causes of heart problems, and we were able to design a signal processing filter bank type system. We call it abnormal beat synthesizer, that can map a normal beat into an abnormal beat. SP supraventricular beat here is an abnormal beat. With that degradation system in signal processing, I think I have some examples here. Let me show you there. Oh, these are some signals that we were able to synthesize. These are synthesized, these are real, these are synthesized, these are real. If you just compare the shapes, you see that we're able to mimic this, the real beats as close as possible. And then we have some results here that this really came up to be one of the best techniques at the time, with more than 64,000 ECG beats. We were able to get a FAR of false alarm rate of 0.45%. If you look at the confusion matrix, we're recognizing most of the normal beats as normal beats and very, very, very small minority as abnormal beats. So the false alarm rate is really, really small. Okay, I'll end up with these couple of slides or 3 slides and then turn it over to Jenny. So our biomedical analysis team here is led by our PhD student Mortaza Zabihi. We are collaborating with a postdoc from Aalto and a couple of professors, one from Northwestern, Agalos Kostagalos, probably some of you know, and Serkan Kiranias from Qatar University. With these guys, we were participating in several international challenges, and we have been coming with very nice and very good results. The first one is in 2015. It's a brain-computer interface challenge where we were ranked number 3 in that challenge. The second one was more about ECG. Actually, it was exactly PCG. This is a heart signal that is measured through the microphone without any LEDs. And 48 teams were participating in the challenge, and we were number 2. And the last challenge last year, we were the first one among 78 teams worldwide, with famous teams from famous universities like Stanford, MIT, EPFL, Philips, North America, Cambridge, and so on and so forth. So we're very happy with those results there. This is the book I told you about. Both books are in your library, at least the database says that you have them. And in summary, we are developing novel algorithms for signal processing, for artificial intelligence, for machine learning. We're applying them in different types of applications. And Jenny now will show you 3 projects where we are using signal processing, computer vision, and machine learning to solve some of the pertinent, interesting problems. Any questions? Or we let her go. Yeah, go ahead.
Excuse me. I have one question regarding to the data generation about the cardinal disease.
About?
The latest project you showed.
Uh-huh.
The data, you use the algorithm to generate the cardinal disease data for the patient does not have history record
Yes.
of disease.
Yes.
How can you guarantee the generated data is accurate?
Yeah.
How can you guarantee the model you train is how to test?
Yeah.
How to
So
test
the question was about this work here. When we generate data, artificial beats for a healthy patient, how do we guarantee that the synthesized ones are accurate? Okay, that's your question is? How do we guarantee that what we synthesize is accurate? All right, so we play the cat and the mouse and cat game. So we have a lot of data coming from healthy people, and we have also data coming from unhealthy people. The data that comes from unhealthy people has good beats and also bad beats. Well, we just make sure that we pretend that we don't know the bad beats, and we try to predict them. So we have a sequence of good beats all the time, and then a bad beat is coming. Are we able to predict that? Of course, we don't see those bad beats at all. We never use them in our training, right? So we can play those things, and this is how we are able to fit this into a system where it would be like sitting in your wearable and looking at your heartbeat, and then the first instant that your heart starts beating in a wrong manner or abnormally, it will give you a warning. Okay? All right, perhaps we move quickly then to Yendi's presentation, and then I'll be able to answer questions if you have any.
And I think the second issue is that you generate many possible kinds.
Exactly.
Not just like one beat, but you have a big library of how it could look like.
Exactly. So it's not a single beat that we're generating out of the bad ones, the bad beats. Do you want to use the pointer or?
I don't need that, but I need the microphone.
Yeah.
And where can I put this? I don't have a good place for it. Can I just keep it on the table?
Or maybe
Well, I can just hold it. Okay, hello everyone. So my name is Jenni Raitoharju, and I'm a postdoc in Moncef's group, and I will now give you an overview of 3 projects that we are currently working on in our group. I had no idea what's your background, so the description will be quite high level without technical details, but you are then welcome to ask questions about the specific methods we are using here. So, few words about me. I finished my PhD last year in March. At that time I was also working with this particle swarm optimization that Moncef was telling about. But after that I have been involved in many different projects and helped supervising our master and PhD students. So now I have expanded my range of research to these many different machine learning topics. Yes, and now I will concentrate on these 3 projects, VIRPA-D, aColor, and Detect, and give some, not the whole projects, but some things that we are doing there. First is VIRPA-D. This is a huge project with a big consortium. Actually, Matti there is one of our collaborators there. I think we have like 14 companies and 4 universities, or 10 companies. Okay, I was remembering it wrong. But anyway, I will not describe the whole project here, only a tiny part that we are doing in our lab. But this project is about intelligent and empathic buildings. We want to create new kinds of services for the people who are using the buildings. But what we noticed there, that many of these possible services, they want to have this information that what are these users actually doing? Where are they sitting? How are they moving? Are they being happy? Any of this information. So this is what we want to do. To use visual information from cameras, also other kinds of sensors to give this information that can be then used to better serve these services. And it happened that they planned in another project in our university that they will install 500 of these Raspberry Pis around the university. They are these small computers with camera in them, and they want to use them to analyze the similar things. This is not yet done, but we wanted to start preparing for it. So we installed 5 of these Raspberry Pis to our office. This picture is from the office. And then we started studying different techniques, how we can actually exploit this data that we are getting from. And we had some very simple questions that we want to find out. First of all, like how many people do we have in the room? This of course requires that we need to detect the persons from the cameras. But then since we have many cameras, we don't only want to count them separately, but being somehow able to tell that this person in this camera is the same person that we are seeing in the other camera. And because we will have 500 of these cameras, we didn't want to specifically use the position that, okay, I know that they are the opposite, so now based on the location it has to be the same person, but we want to use just the content to recognize that, okay, now we have the same person in these both cameras. And then we want to go further. We want to recognize these people. In our office, we can just use face recognition to try to see who is there. And also, even if we don't know the personality of a certain person there, we want to be able to follow his actions or her actions so that we know that, okay, the same person was here 15 minutes ago, so you can re-identify this person even without knowing who he is. Then tracking is important for many of these applications. You want to know how they are behaving in the room, so we have tested tracking methods. And finally, we have been evaluating these edge computing techniques, can we actually use this small computer on Raspberry Pi to do some of these things, or do we have to send everything to a big cloud and then do this analysis there? So we had noticed that we have some challenges here. First thing was that this is real data, so when we took the state-of-the-art methods and tried to see how they work, we see that, okay, the accuracy in real life is not what they report in the papers and the public data sets, which are good quality, but because we have occlusions, we have shadows, then we have to put the cameras where we can attach them. You can have high cameras, low cameras, so you have variance in this angle of view and so on. And of course people are not just walking or something, they do different things and it makes things more complicated. Again, we don't want to use the location of the cameras. So then we have now gone a bit further in this and we noticed that, okay, it's still relatively easy to detect persons in like a single camera. Tracking, it's doable, and also face recognition, unless if the face is pretty good, like not totally sideways, but somehow toward you, we can catch this. But then the main challenges are this ray identification, both in like between different cameras. How can you match the two persons there? And also this edge computing, we noticed that these Raspberry Pis are weaker than expected, so they cannot really do much in real time, which we wanted to do. But we want to continue further to see what we could achieve there. Now I have my video slide. Let's see if it works this time. Nice. So here we have example of 3 different detection methods. This yellow one is kind of state-of-the-art method and it works nice, but it certainly cannot be run real-time on Raspberry Pi. So on the lowest one we have something that can be done there, but you can see all these false detections on the table and so on. So these kind of things we're dealing with, how we can then still somehow use this maybe to detect some important cases when we send the data for further analysis for the cloud or so on.
What do you do here to do the detection exactly? Does that describe your
This
procedure,
is just
your background?
Yes, just because we know the background from the camera, we have a fixed camera position, then we just see like the moving things, subtract the background, do this stress holding. So this is a simple technique, but also it has the problems. Here's an example of this re-identification problem. Here we are using CNN features to try to match 2 detected persons. And the top row shows that there we were successful. We have this is the Serkan Kiranias, the visiting or the collaborator from Qatar University. So he was matched correctly. But then whenever we have this kind of situations, the girl on both pictures is the same, but because you have a different pose, in the other one you see the whole body and the other one shows only the upper part of the body, these CNN features are not able to match these. So this is what we are now working on to improve these problems here. Then I move to the next project. It's called Autonomous and Cooperative Offshore Robotics, aColor. This is also a bigger consortium project. And we actually have here this autonomous boat. And also we are dealing with drones and this autonomous small submarines. And they try to communicate with each other. We started with like just having a fixed route to the neighboring island, try to follow this, avoid any hitting, not kill anyone. That was our first target for the project. But the ultimate target somehow is to use these to rescue stuff, rescue operations. So when you hear that on certain area someone is overboard, you could go there and then also use the drones and the submarine to try to help in this area to find the person. And again, our part here has been this visual analytics, also partially this multimodal analytics to combine data from different sensors. But this project started in January, and we actually the first half of the year we were building the boat. So we installed all the equipment there, and it took a lot of time before we even started the actual work of analyzing the data. Here you see some of the sensors we put to the boat. We're mainly using the camera and thermal camera in our experiments and see what we can achieve there. So what we started with was that, okay, we don't want to hit anything. We have a person there now who's like a backup and can do something. And so we decided that, okay, we will just stop if anything that is not water comes above us. So that's why we just segmented the water and everything else. Here's a video of that. So the red one we have defined as water, and it can pretty well find everything else that's like something else than water. There you actually saw the snow as well. This was...
It's not the Red Sea, it's still our lake.
Yeah, this is...
Pseudo-coloring.
Not a bloodbath.
Yeah, we didn't kill anyone. This was...
No
I'm
way.
glad to hear that.
What happened? Here I will just show the example. Here we don't have any detection yet, but we are now starting to merge the information from normal camera and thermal camera, because especially we want to detect any people. And we noticed that this can be easier in this thermal camera because, whoop, why is it not playing? So any people in these pictures, they're very bright spots as long as they are above the water. Of course, if someone is there, almost drowned person, it will not be that easily visible. But this is our current motivation. We want to combine the two camera views, normal camera and thermal camera, and create a model that can be used for collision avoidance and navigation. And the final project is, oh, it has so long name that I will not even read it. But it's called Detect. And the main thing here that is that in the river and lake bottoms, they have these small creatures, macroinvertebrates. And they are actually pretty important in the sense that whenever you have some changes in the lake, some environmental problems, for example, these bugs, the species that you find there, they quickly react, they change to different ones. So that's why there's this European Union legislation even says that you have to regularly evaluate which species you find in each lake. And this is something which is, of course, a huge task. Someone have to go and collect the bugs. And further, the identification task is something that you need like a 4-year university training to be able to do that properly. And this is what we would like to help, that not so many experts are needed anymore, but we could do some of this stuff automatically. And yeah, we are concentrating especially on this Benthic freshwater macroinvertebrates in Finnish freshwaters. But here are some examples how they look like. And you can see that it's a pretty hard task. So even if I have been dealing with these bugs for many years now, I have no idea how to tell these different taxa separate from each other. And also, this is something that the experts cannot do from the images. They need to have their microscope, and they need to be able to like pull out the leg and see something and this kind of things. So this is a challenging task because they're so similar.
These are microscopic, or is this life
This is
size?
a normal camera.
Life size.
Yeah, they are varying from like this size to biggest or
So
something
this is
this.
real size.
Real.
half a centimeter to about 2 or 3.
Yeah, biggest one I saw was like something like this, but not many are this big. So what we did in this project, we first of all built this imaging system. We had 2 cameras in 90-degree angles, then this test tube filled with water. We can just take, someone has now collected the bugs, we can just drop them one by one to the tube, and when the bug is falling down, slowly these cameras are taking pictures, and then this way we get several pictures of the same specimen, and then we can try to use them all to enhance our recognition rate. So using this system, we have first of all collected some data sets. We had some really hardworking biologists who really labeled these data sets for us so that we can use them for training our system. We have now 2 versions. They are publicly available. The second link is not permanent yet, but this is because they have some updates in the system. But the newer data set, it has almost 500,000 images. For each specimen we have maximum of 50 images. We noticed that it's not helping anymore if you put like 500 images for the same bug to make it a bit lighter. But some bugs, because they were falling so quickly to the bottom of the tube, they have it less. There are 39 classes at the most accurate available level. And what this means is that we have like hierarchical labeling for these. So they have this order, family, genus, species level, and they are not all labeled to the most accurate species level because this was too hard for the biologists as well, but they can put whatever they could say, certainly. This is an overview of the data set. So you see that we have very varying class sizes. And also the hierarchical structure is very varying in the sense that for these 2 orders even we have just a tiny amount of pictures. I will get back to these problems a bit later. But now we did recently this work where we actually compared then these human experts doing this classification task and how these machine learning models can do there. And we of course just compared the accuracy, but in addition to that we wanted to analyze the decision-making strategy that they are using. So, because one of the problems is that the biologists are very hesitant to use any of these techniques in their work because they say that we don't really understand how this network is making its decision, and that's why we don't want to use it. And we want to show them a bit more that what was there different in the ways they do their job and how these neural networks do. So one observation was that these humans are trained to classify these things very hierarchical manner. So they first decide that which order do you have. Then, okay, now I know that it's this order. Then I try to decide which family within that order and so on. So they don't try to recognize the actual species right away. And this turned out to be a bit different for the machines. We tried this hierarchical approach with them as well, so that we trained a separate classifier for each node here, first decide the order, then decide the family within this task. And we noticed that we cannot really even beat the flat classifier that just takes the most accurate level first. And one reason we got here is that this hierarchy is not really based on any visual attributes. They are just relatives. I don't know why, I don't know how this works, but they might not look so similar within the same group of these subgroups. Yes, and one thing is that the current status is that we can clearly outperform any non-expert humans in the accuracy, and also when the experts try to use the images, they cannot tell them apart. But still, when the experts are given the real creature, the microscope, and they can do whatever they want, then they are still slightly above the machine learning level. But so what is the current situation in this project? We have even more images. We have 2 million labeled images from 130 different classes. But there are some problems. We have very unbalanced classes. Some of them have only a few bugs in them. And then we have this like varying conditions. At some point we had to change the camera or the light source that we had. And then we noticed that, okay, we have trained the networks, but after this, the performance is kind of ruined. Then we have some inconsistent labeling. Depends who was doing it. Someone was able to label it to the very species level, and then someone was not able to say it so clearly. So we need to be able to use these labels from different taxonomic ranks. So currently we have only exploited this 500K images in our research, but we of course don't want to waste this huge data set, and we want to find ways to use it more. And then further challenges are that these smallest classes are of course the interesting ones because they can show the changes that are happening. And even more important are these unseen classes. If you start getting new species in your lake, then this is a big change and you should detect it. But it's of course very different for the machine learning model. How can you recognize this when you don't have any training samples? Of course, it's very laborious to collect and label more data, so this is not really an option. And then, so what we should do, we should first of all make sure that our system is more robust for these changes, the lighting, camera, we should be still able to use it. And even these other data sources, so they publish somewhere in Sweden a similar data set with lots of overlapping species, but of course they have a different imaging system and they have different background. So we're dealing with methods to try to use these more efficiently. And some ideas for this hierarchical classification. So here are some of the current challenges we are working on in this. So this data imbalance, how to enhance the performance, especially on these small and unseen classes, and this data variance, how to deal with the possible lighting changes and so on. Unseen classes, can we create some models that will consider our current classes as the known ones, but then give some kind of warning that, okay, this is probably something we haven't seen before, and then an expert could come and check. And some hierarchical classification techniques we're working on with. Finally, how is this picture related to this box? These are actually totally artificial images generated by these GANs. And you see that they are very real-looking persons anyway. So this is now one of the methods that we are considering for this data imbalance problem, that we could train a GAN to generate more training samples for these underrepresented classes in our data set, and we hope that this will boost our performance on these classes. We have some other plans for this as well. So this is all what I have. Here's my email if you want to contact me later, but do you have any questions now?
Come up here if you have any questions for any of us.
Yeah, I have a question. You mentioned earlier the use of both optical and infrared cameras. Do you find it particularly more useful to use an infrared camera at different times of the year, given that thermal cameras obviously work on heat rather than
Yeah, probably, let's say we have always cold enough in Finland that this is not a problem. So all these examples were summertime, and even there, like humans were very clearly visible, easy to spot out from the image. Of course, I assume that this will be even more clear in the winter time. But winter time we cannot drive with our boat because the lakes are frozen. So.
then that you can ski.
Yes, yes.
Any other questions?
Another question?
Yes.
Question for the first project, for the re-identification with CN features. Like, how did you do that? I mean, are you using the?
Can you speak up? Speak up.
Okay. For the first project, like for the re-identification with CN features, I mean, you try to match the same people in a different image, right? Like, how did you? What features are you using to do the re-identification?
We just tried different like networks that are trained to detect people. Then when we have the person detected, we just extract the CNN, like the second last layer, and try to match this. But what we assume is that, of course, these like people detection networks, they learn to ignore your clothes, for example, because you should not confuse that this is not a person because the shirt color is strange, so they will not really pay attention to these things. But they would, of course, be very useful for us because, especially for the two cameras at the same time, this is probably the best cue that you can have, that these clothes are the same than from these. So this is what we are now trying to like train a bit differently, that so that we don't just try to train it to detect persons, but train it to separate persons.
I haven't read your excellent book, so but I have a question about do you have any comments from singular processing perspective to compare, for example, why the state-of-art, the residual network, right, works much better than the traditional like VGG, like LXLET, those purely forward. Right?
Say again.
There's different type of neural networks, right? The one you introduced is more like a multi-layer perception. Yeah. But in the state of art, people also developed different topology, especially the residue network. Yeah. When you add these residues, and in terms of optimization, of course it can remedy the gradient vanishing problem. But I wonder whether there's some other perspective from signal processing, how those residue connections can improve the performance so much.
So the question is about the different types of topologies of networks that people are now using in, say, deep learning. What we showed you here is a simple MLP, multi-layer perceptron, where we apply particle swarm optimization or multidimensional particle swarm optimization to design the topology, the optimal topology, and the optimal networks, optimal network parameters. Now, if we go to more complicated networks, then things become much more difficult because topology get much bigger, much more variant. The variations is much more like bigger there, and so we will need to find better optimization schemes to design these networks. And sometimes we're working on that. We are trying, one of the things we're trying to introduce is non-linear operations in the neuron level, okay? There is no reason that a network would have a linear summation, sum of the weights and multiplied by the input from the previous layer and then some nonlinear activation function. It can be a nonlinear operator as well. But again, the challenge here, how to find these optimal operators, or how to find the optimal set of nonlinear operators and so on. Believe it or not, the problem of vanishing gradient does not only apply to bigger network, it is also a problem in MLPs. And when you read the book or you read the papers related to the book, you will find lots of problems where the gradient gets stuck in a local minimum. And we proposed several alternatives, several ways to deal with that problem. One of them is called simultaneous perturbation. So from statistical signal processing, when you go to the gradient, you have a gradient of, let's say, several dimensionalities. You perturb, you inject a certain noisy signal so that the gradient will not be exactly what the real gradient is, but will be a perturbed signal around it. And we are hoping with that perturbation to kick out the descent from the local minimum. Another approach that we tried there was to look at different dimensionality one at a time and explore these dimensionalities. And so we called it a new or artificial particle that we incorporate into the system that collects the best and optimal performance per dimensionality. Well, this works nice, except that it has one big restriction. The restriction is that your objective functions need to be separable. So I can find my objective function that is a function of x, y, z, or many other things, as a function of f of x, a function of f of y, a function of f of z. And this doesn't happen all the time when you have complicated functions. So I think to answer your question and to be brief, there's a lot more work to be done in designing complicated, complex network in an optimal way. We're not there yet. We just start to like scratch the surface at the moment.
Yeah. Any other questions?
You're behaving like our Finnish students. They don't ask any questions. We're in the U.S. here. Frequently ask questions.
So, if there's no other, okay.
Matti has a question.
Oh, this is more like comment, just throwing the topic to you. Can you elaborate a little bit the research collaboration and how you do research universities, other universities, and the business side?
So the main reason we're here in the U.S. this time is because of the center, NSF, National Science Foundation center called CVDI, Center for Visual and Decision Informatics. This center is a collaboration between several universities in the U.S. and in Finland and many companies, both again in the U.S. and in Finland. We have two representatives of companies from Finland. And what we do here is the company guys give us some research challenges. We don't call them problems, we call them challenges, and we try to propose solutions for them. Sometimes they offer us infinite data or access to their data. We play with that, we show them some possibilities, and then we interact with them at various levels. We have companies that we work with almost on, let's say, weekly basis. We have some other companies that we interact with maybe once every month or a couple of months. And there are two major meetings per year, the fall meeting and the spring meeting, when all these guys come together and the university guys will show what they have done and these companies collaborate. In Finland we have a lot closer collaboration with our industry partners. We have a government agency called Business Finland that supports our research when we collaborate with companies, and we build projects together where the companies give us seed money and then the Business Finland will give us the remaining, the matching funds to carry out the research work. And the work is organized again really in sort of consortia where we share the findings all together. We have a sort of consortium agreement that we agree ahead of time who is doing what and who is going to use the results for what purpose.
How do you deal with the IP?
IP is not a problem for us whenever we have, well, two types of issues, two types of collaboration. One is a university to business direct contract. That way, in the contract, the company can say, I will own everything. The second one is where in the consortium agreement that we agree that whatever we do is going to be either open or we will sell it to any company in the consortium at what we call market price. And Matti has a comment there.
And also, GET as a company is participating and also funding the research. And also our competitors are doing the same. So we are in collaboration with our competitors in the research center. And there we see that the most of the research is pre-competitive research.
Yeah.
Making basis for our future competition. But these guys, they do the work, we have funds, that we have something to compete with. But it means that we don't require that they would provide IPs. They provide research which is useful for our future purposes. But not on a stage that they are products which can be patented and also having IP. But also could be so. But that we are not requiring.
So basically our funding sources dictate the type of IP and how to share the IPs, and we must obey those. That's the main thing. Okay, well, thank you guys for being patient. I hope this was useful.
Thank our speakers again.
We're gonna need your PDF file. We will need your PDF file.